In today's class and video, we are going to look at molecular weight standards in gel filtration and the plotting of the gel filtration calibration or standard curve. We'll start our introduction by looking at what molecular weight standards are in gel filtration. So molecular weight standards are reference or standard materials, in this case proteins, with known molecular weights that are used to determine the molecular weight of unknown proteins. And this can be done by comparing the elution volume or the partition or the distribution coefficient of the unknown protein with those of the known molecular weight standards run in the same column on a calibration curve. The molecular weight unit is expressed in Dalton or kilodalton. So let's see how to plot the gel filtration calibration curve or the gel filtration standard curve. So the first thing to do is to run a series of protein standards of known molecular weight through the gel filtration column. So when we are done with this, we identify the elution volume for each of the standard proteins and then calculate the partition coefficient or the distribution coefficient for each of the standard protein by using the formula VE minus V naught or divided by VT minus V naught. So where the VE is the elution volume of the molecule, the V naught is the void volume of the column, and the VT is the total volume of the column. So once we are done with this, we plot the KAV values on the y-axis as shown over here against the logarithm in base 10 of the corresponding molecular weights on the x-axis as shown over here. So once we are done with this, we find the linear regression of the plotted values by finding the line that best fits the data point. So from this graph over here, this is the line that best fits our data points over here. And after finding this line that best fits the data point, we generate the equation of the line in the form of y equals ms plus c. And this can be done by using Excel. So from this calibration curve, this is the equation of the line for this calibration curve, which is giving us y equals 0.4512 s plus 3.4656. So where y happens to be the KAV values, then negative 0.4512 is the slope, and s is the logarithm of the molecular weight, which is on the x-axis, and the 3.4656 is the intercept. So once we are done plotting the calibration curve, we determine the distribution or the partition coefficient of our unknown protein by running this unknown protein through the same gel filtration column used for the standard proteins and measuring its elution volume. And what we have to note is that with the knowledge of the unknown sample elution volume, we then calculate the partition or the distribution coefficient using the formula VE minus V naught divided by VT minus V naught as explained earlier. So let's see how we can estimate the molecular weight of the unknown proteins in the gel filtration. So the first method is to plot the calibration curve of the partition coefficient values of the standard proteins on the y-axis against the log of their respective molecular weights on the x-axis as a calibration curve. And once we are done plotting the calibration curve, we determine the KAV value of the unknown protein by running it through the same gel filtration column and measuring its elution volume. And by comparing the KAV value of the unknown protein to that of the known proteins on the calibration curve, we can extrapolate the molecular weight of this unknown protein by using the equation of the line. So this is the first method by which we can estimate the molecular weight of an unknown protein. The second method is to plot the ratio of the elution volumes to the void volume of the known molecular weight standards on the y-axis against the logarithm of their respective molecular weight on the x-axis as a standard or a calibration curve. And once we are done plotting the calibration curve, we determine the value for the ratio of the elution volume to the void volume of the unknown protein by running it through the same gel filtration column. And once we are done with this, by comparing the ratio of the elution volume to the void volume of the unknown protein molecules to those of the known molecular weight standard or the known proteins in the calibration curve, we will be able to extrapolate the molecular weight of the unknown protein by using the equation of the line given in the calibration curve. The next and the third method is to plot the elution volumes of the known molecular weight standards on the y-axis against the log of their respective molecular weights on the x-axis as a calibration curve. And once we are done plotting this calibration curve, we determine the elution volume of the unknown protein by running it through the same gel filtration column. And by comparing the elution volume of the unknown molecule or protein to those of the known molecular weight standards on the calibration curve, we will be able to extrapolate the molecular weight of the unknown protein or molecule from the calibration curve by using the equation of the line obtained in the calibration curve. So let's take a question and use the various calibration curves to determine the molecular weight of the unknown protein. So the question says, in a gel filtration chromatography, the elution volume for blue dextran is 17.5 mils. And if the total volume of one complete run is 95 mils, use the table below to plot the gel filtration calibration curve and also determine the molecular weight of an unknown protein with the elution volume 69.3 mils. So this is the table given over here. So this happens to be the molecular weight for our standard, and this is the log of the molecular weight for the standard, and this is the elution volume for each of the known molecular weight standard, and this is the calculated partition or the distribution coefficient value for each of the molecular weight standard. So for the first method, we are going to use this graph, and it is a calibration curve which is being plotted by plotting the partition coefficient value for each of the molecular weights on the y-axis against their respective log of the molecular weight on the x-axis. And from this calibration curve, this is the equation of the line, which is giving us y equals negative 0.6824s plus 3.6742. So from the question, we know that the elution volume for the blue dextran, which is 17.5, is the void volume, and the total volume given in the question is 95 ml. So using the equation of the line, which is giving us y equals negative 0.6824s plus 3.6742, we know that our y is the distribution coefficient, or the KAV or the KD, which is giving us the elution volume minus the void volume divided by the total volume minus the void volume. And we also know that the negative 0.6824 is our slope, and the S is the log of the molecular weight of the standards on the S axis, and this is the 3.6742 is the intercept. So if you are to substitute the values, which is the elution volume and the total volume and the void volume, in this equation, we will get our y to be 51.8 divided by 77.5, and this is equal to 0.66839. So making S the subject from the equation of the line, we will get 0.6824 H to be equal to 3.6742 minus S, and if you are to substitute the value of the y, 0.6824 H to be equal to 3.6742 minus y, and if you are to substitute the value of y, which is 0.66839, into the equation, we will get our H to be equal to 3.00581 divided by 0.6824. So our S will be equal to 4.4048. But what we have to note is that from the calibration curve, our S is equal to the log of the molecular weight. So if you are to determine the molecular weight, we will have to take the anti-log of the S value. And taking the anti-log of the S value, we will get the molecular weight to be the anti-log of 4.4048, and this will be equal to 25,398 dalton as the molecular weight for the unknown protein. So now let's also use the second calibration curve that we plotted by plotting the ratio of the elution volume to the void volume of the molecular standard weights on the y-axis against the log of the molecular weight on the s-axis to calculate the molecular weight of the unknown protein in the question. So again, from the table, this is the elution volume for each of the molecular weight over here. So to calculate the ratio of the elution volume to the void volume, we just divide the elution volume for each of the molecular weight by 17.5, which is the void volume. So if you are to do that calculations, this will be the values for the ratio of the elution volume to the void volume for each of the molecular weight. Now, so let us look at the equation of the line for this calibration curve. The equation is giving us y equals negative 3.0219s plus 17.271. And what you also have to note is that from this calibration curve, our y is equal to the ratio of the elution volume to the void volume, which is giving us VE over V naught. And from the question, we know our void volume to be 17.5 mils and the elution volume to be 69.3 mils for the unknown protein. So if you have to substitute these values into this equation, we will get our y to be equal to 3.96. So now making S the subject from the equation of the line, so we will get H to be equal to negative 13.311 divided by negative 3.0219, and this gives us S value to be 4.4048. And once again, what we have to note is that the S value on the calibration curve is the log of the molecular weight. So if you want to calculate the molecular weight, you will have to take the antilog of the S value, and taking the antilog of the S value, which is 4.4048, we will get the molecular weight to be 25,398 dalton. And this is also the same as the previous answer that we had using the other calibration, where we plotted the partition coefficient against the log of the molecular weight. And finally, let us also use this calibration curve to also determine the unknown protein for the. So let us use this calibration curve to also determine the molecular weight of our unknown protein with the elution volume 69.3. So from the table over here, these are the elution volumes given for each of the molecular weights over here, and this is our calibration curve. So from the calibration curve, the equation of the line is giving us y equals minus 52.883s plus 302.24. And from here, we know that our y is equal to the elution volume, which is given at 69.3 from the question. So if you are to substitute the value for y, which is 69.3, into the equation of the line and make s the subject, you will get s to be equal to negative 232.94 divided by minus 52.883, and this gives us the s value to be 4.4048. And once again, we know that the s on the calibration curve is the log of the molecular weight. So if we want to determine the molecular weight, we take the antilog of the s, which is 4.408. And if you have to do that, we will get the molecular weight for our unknown protein to be 25,398 Dalton. So these are the three different ways by which we can determine or calculate the molecular weight of an unknown protein using any of the three types of calibration curve. And what we also have to note is that sometimes a question will limit you to a particular type of calibration curve. So whenever you are solving a question, you have to take note of that. So let's look at examples of molecular weights that are normally used in gel filtration chromatography. So we have the lower molecular weight markers, and these are the examples. We also have the intermediate molecular weight markers, and these are also some of the examples. And finally, we have the higher molecular weight markers, and these are some of the examples. So these are basically some of the molecular weight markers that are used to determine the molecular weight of unknown molecules in chromatography.